Hey guys, this is Algebra 1, Lesson 5-2, piecewise defined functions. In this lesson, we'll be able to graph and apply piecewise defined functions. New vocabulary, piecewise defined functions. So what is it? We'll explore the concept, the idea, and learn what it is exactly. Let's look at explore and reason. Since the table here is not complete, let's switch to another panel. Okay, I already have some notes in it, but look at the situation. In a relay race, each runner carries a baton for an equal distance before handing off the baton to the next runner. So if you already know relay race, you probably already know relay race, but basically you have a team and there are many runners that will carry a baton, one at a time. So if you look at this chart, we have 4 runners. They're gonna carry a baton and run with it. They're gonna give the baton to the next player, and the next player takes the baton and runs with the baton. So the baton will going to travel the entire distance, but the runners take turn. Okay, so if you look at this chart, there are 4 runners. Runner 1 starts from the start 0, runs 0.25 miles, quarter mile, in 3 minutes. And then from there, this table is for the path of the baton. So we're not talking about each runner, we're talking about the entire trip for the baton. Okay, the players are going to change, but the baton will keep going. So runner 2 ends with total distance 0.5. They all run the same distance. They're all going to run quarter mile, but their speed is different, right? Every person has different speed. So runner 2 runs the quarter mile in the next 2.75 minutes. So a little bit faster than runner 1. But total minutes with runner 1 and 2 is going to be 5.75 minutes. Okay, and so on. So runner 4 finishes the mile race. It's a mile race. It's several kilometers and kilometers. So it's pretty long. And the time is 11.5 minutes total for all 4 runners to run the whole mile together, each at a time, one at a time, takes 11.5 minutes. And if you look at the minutes, runner 1 ran the distance in 3 minutes. Runner 2 ran in 2.75 minutes. Because if you add 2.75 to 3, you get 5.75. And from 5.75, if you add, what's the difference? If you add 3.25, then you will get 9 minutes total. And then from 9 to 11:50 plus 2.5, right? So who ran the fastest? The smallest number for the minute would be the fastest, because that means they ran the same distance in that many minutes. So runner 4 is the fastest, and then runner 2, and then runner 1, runner 3 is the slowest, because he or she finished the quarter mile in 3.25 minutes. So part A, graph the distance traveled by the baton as a function of time. How is the speed of each runner represented in the graph? So you're going to put these into each points. But if you connect the points, it's not going to be a straight line. Let's look at decimals. Okay. So these are the 4 points we have. If we draw a straight line through the first point, we get a straight line, but do all the points lie on this line? No, they're not going to form a straight line. So it looks like it's close to a best fit line to the points, but there's not going to be exactly one line that goes through all the points, right? One straight line. So what do? Well, another way, instead of using the best fit line, another way to graph it is to connect all the points in a straight line, but different line segments. So you should, this is not an accurate graph, but you should graph all the points like we did in Desmos and graph each line as a segment. So they're gonna have 4 different segments, and they're all gonna have different slopes because all their speeds are different, right? But X is gonna represent time in minutes, Y is going to represent distance in miles. Okay? So that's part A, graphing. Part B, who is the fastest runner? We talked about this, right? Look at the slope. The shortest, the fastest runner will run the quarter mile, the same distance in a shorter amount of time. So the less the number is, the less your slope is, the greater the slope, because the slope is distance over time. The greater the slope, or the less your number of slope is, the less time you need to you need to cover the quarter mile, the faster they are. So this is going to be, the slope is going to be this is not the slope. Whoops. I erased some table, but that's fine. 0.25. You're going to divide 0.25 by 3, 0.25 by 2.75, 0.25 by 3.25, 0.25 by 2.5, or you can just divide the numbers, the values of Y by the values of X. Okay, but runner 4 is going to be the fastest. So B here, runner 4, he or she runs 0.25 miles in 2.5 minutes only compared to other players. It's the fastest. Okay, part C. How is the graph of this function similar to the graph of a linear function? Okay. So it kind of looks like a straight line. It's close to a line. They're lines, but they're not going to be one straight line, right? So the graph is similar because it's made up of connected segments that look like a line, but each segment has a different slope, so that's why it's different. Okay, the graph has connected segment that look like a line, but each segment has a different slope. So that's why it's similar, and this is why it's different. Okay, moving on to example 1. So we're going to start talking about the piecewise function. So if we have a graph that is one function, but you cannot have one straight line to cover all the points in the function, you can graph it with piecewise defined functions. Okay, so let's try to understand piecewise defined functions in example 1. And keep in mind what the key features of piecewise defined functions would be. So we have an absolute value graph here. How is function of X f of x equals 2 times absolute value x related to a linear function. Okay, look at this graph. It looks like a V. We have two different lines. Do you see that? Two different straight lines that have different slopes. You see that? The left one seems like it has a negative slope. The right side seems like it has a positive slope. If you divide this function in half on the y-axis, you can reflect those two lines, right? So this absolute value function is a piecewise defined function. Here's the definition. A piecewise defined function has different rules for different intervals of its domain. So for domain, all the values of x, you're going to describe the function with restricted domain. So f of x, the original graph was the absolute value, right? This is the original function. But you can write this, you can also write this as a piecewise function. So there are two ways to write absolute value graph. Just use the absolute value sign, or you can write separate equations for different domains. So if you look at the left side, all the points on the left side of the line is going to be in this one line, right? And it's going to have the same slope. But how can we define them? These points all have negative x values, right? And positive y values. But we're going to define it using the domain. So x greater than or equal to 0, x less than 0, right? So if we include 0 as a positive number, then we're not gonna include that for the negative numbers. So when x is greater than 0 or equal to 0, so all the positive values on the left, on the right side, the graph is gonna be 2x, right? It has one slope. But once we have domain less than 0, it's defined as negative 2x, okay? So this part on the bottom, they're cut off. It doesn't belong to the function, okay? So we're gonna restrict it by the domain. All right, it sounds a little bit complicated right now, but the whole idea is that you cut them into pieces and write equations for each line segment, and define them by the domain restriction, like from what number to what number for x is that line segment there. Okay, so the function f of x equals 2 absolute value x has two pieces over two intervals of the domain, two line segments. For each interval, the piece is a linear function. Okay. So looking at example 1, can you try this problem? Try number 1. Express f of x equals negative 3 absolute value x as a piecewise defined function. Okay, it's very similar. Look at example 1 and see if you can solve it by yourself. Come back when you're ready for answers. So this is one way to write it, right? Absolute value function. Write it as a piecewise defined function. Write an equation for each line segment, divide them, and define them by domain. Okay, are you ready? All right, first of all, you can use Desmos to see how it looks like. F of x equals negative 3 absolute value x. You can type in this. Looks like this. It's flipped, right? It's reflected on the x-axis, and it has a vertical stretch. So you can divide this in half by the y-axis again and figure out the slope. Look at the slope here. Pick a point. This point seems like a good point. 0.5, negative 0.5, comma negative 1.5, and 0, comma 0, right? So then you can use the slope formula, or you can count how many times, how many blocks you're going up, right? You're going up 1.5 up for the y value, and you're going to the right 0.5 unit. This is a positive slope. Or if you're counting from here to here, you're going left, so negative 0.5, right? But you need to go vertical first. So go down negative 1.5, and then negative 1.5 over negative 0.5 would be positive number, right? So what is it? 1.5 divided by 0.5 is 3. So your line here could be y equals 3x. You see that? It maps exactly on the left part of the function, right? But you have to cut it. You don't want this part above, right? It's not supposed to be part of the function. So we have the equation now. We have to cut it. How do we do it? We're going to say, for all the domains, x, where x is less than 0, right? And then you cut it. You see my line? Okay, so we figured out the left side of our equation. How about this side? Well, you count the slope again. You go down 1.5. So negative 1.5 over positive 0.5. It's still going to be 3, but it's negative 3. It's a negative function, negative line. So y equals negative 3x for all the positive values of x. So let's cut this line as well by using bracket. X has to be greater than equal to 0. You see that? So if we, so that's our positive side. If we have both of those equations and then let's hide our absolute value, does it make our absolute value function? Yeah, it maps exactly on it. So we figured it out. We just have to write it together in a big bracket. So how do you write this down? You're going to say f of x could be written in 2 equations. First, f of x is already range, right? So you don't have to write y equals again. You just have to write the equation here. This is like, oh, y equals, you need to write equation. So 3x when x is less than 0, right? And it could be negative 3x when x is greater than or equal to 0. Okay, that's it. So you have to have different equations for different line segments, and you need to define the line segments with the domain. Where are you going to use it? Where are you going to cut the line? Okay, so all the negative values, you use the line 3x. All the positive values of x, you use the equation negative 3x. Okay, that's example 1. All right, moving on to the next page, example 2. Graphing a piecewise defined function. How do we graph if we have a piecewise defined function as an equation? So let's figure this out. What is the graph of x plus 1 when x is less than or equal to 2, and negative 3 over 2x plus 6 when x is greater than 2? So we're gonna look at one by one. So the top part says the equation is y equals x plus 1. Can you graph that? Yes, you can. But once you graph the y equals x plus 1 equation, which looks like it's this one, the red line, you need to cut it where your domain ends. it only applies when x is less than or equal to 2. So when x is greater than 2, you have to erase the graph. Okay, you don't use the first one. When x is greater than 2, you use the second equation. Y is equal to negative 3 over 2x plus 6. So starting from 6, count your slope, negative 1, 2, 3 over 2, 1, 2. And then 1, 2, 3 over 1, 2, right? But you do not draw a line here. You're going to start from this when x is equal to 2. When x is greater than 2, you're going to use this line. So draw the line until your domain ends. Okay, and draw the line draw the second line where your domain starts. Okay, can you have both of them equal to 2? No, because why? What is a function? In order to be a function, there's only one y value for each x value. So if you have 2 points, 2, 3, and 2, something else, then it's not going to be a function. So they're going to equal to the same value, but there are cases where you start at a different point. So just make it into a habit that you do not overlap your domains, okay? And where do you know the domain is the function increasing or decreasing? You need to look at the slope. Slope for the first equation is positive 1. Slope for the second equation is negative 3 over 2. If you have a positive slope, you have an increasing function. That's a positive slope. That is a negative slope. So that's increasing until x is equal to 2. And then from x is equal to 2, graph is decreasing. Okay? So try number 2, graph the following function here by yourself and see if you can do it by yourself. Oh, this one, they're not gonna be continuous. So why don't I explain it to you as well? Okay, so in this graph, first we're going to graph x is x minus 2, right? The first one. Y is x minus 2. So start from start from negative 2 here, and then you have a slope of 1. So it increases by 1. That's negative 2, negative 1, 0, 1, 2, 3, and so on. Okay, and you go there until x is less than or equal to 1. X is 1 is right here. So you do not graph when x is greater than 1. So you're gonna ignore the points greater than when x is greater than 1. So to the right of this point, you're gonna ignore, okay? And x is less than or equal to 1. Okay. What about the second graph? Y is negative 2x plus 3. You start from 3, y-intercept 3, and count your slope negative 2 over 1, negative 2 over 1, negative 2 over 1, negative 2 over 1, and so on. And now you notice it starts at a different point over here, okay? You graph this when x is greater than 1. So x is 1 is here. So you can start from 1. Wait, I don't think I should graph that one. I'm going to stop here, right? You have a different starting point, but which one is the right point? Because you cannot have 2 y values for one x, or else it's not going to be a function. So in this case, what do? Well, check your inequalities. X is less than or equal to 1 versus x is greater than 1. So 1 should be your first or second graph, the first equation. So it sticks with your first equation, but not your second equation. It's not included in the second equation. How do we indicate that? By an empty circle. So when x is 1, where you're starting, draw an empty circle over here. Okay? And this is the final answer. Okay? Make sure this is a closed circle and that's an open circle. And you can erase all the other unnecessary points. Okay? That was try number 2. All right, let's look at example 3. Analyze the graph of a piecewise defined function. Cheyenne's mother is reviewing the monthly water bills from the summer. Each monthly bill includes a graph like the one shown, which reflects the different rates charged for water based on usage. Several relatives visited Cheyenne's family in July, and their water bill more than doubled. Assuming that the water consumption did not double that month, what is a possible explanation for the increase? And now we need to analyze. Okay, so look at the graph. The y-axis represents the water bill. The x-axis represents the gallons of water by 1,000. So from 0 to that's 6, so that must be 5, right? 5,000 is tier 1. And water bill is from 0 to $5. Okay, and then tier 2 is gonna be from 5,000 gallons of water, not including 5,000, till 10,000 gallons of water. And then tier 3 starts from 10,000 gallons of water until forever. Well, until wherever, the greater numbers, right? But water bill is going to increase from tier 1 to 3. Okay, the rate changes. So if you just use a little bit of water and you stay in tier 1, then the maximum charge would be this high. Okay, but if you use more than 10,000 gallons of water, then you're gonna be at a minimum charged $30, and then it's gonna increase at a higher rate. Okay, so you need to be able to define each segment like that and see how you can analyze it. What is a possible explanation for the increase? Why do you think the rate changes? Why do you think the rate, the speed increases? So tier 1, it slowly increases. Tier 2, it kind of speeds up. And then tier 3, it increases really fast. Why do you think so? Okay, so it doesn't say here, but maybe it's because the company might want to charge higher rates for greater levels of water consumption because it wants to penalize extra water use during a drought. It's if you're going through a drought, then water is really important. And if you're using a lot more water than you're supposed to, then the water that you spend for extra, it's gonna be charged more. It's gonna be more expensive than what you really, really need. Okay, and it could help encourage people to save water by that. So try number 3 is basically about that. Make a conjecture about why a utility company might charge higher rates for greater levels of water consumption. It doesn't have to be the reason I just talked about. Make your own, but don't be unreasonable. Try to come up with a reasonable conjecture. Why do you think it is? Right? So you can have many different answers, but I'm gonna write down whatever I just said right now. So utility company might want to charge higher rates for greater levels of water consumption because it wants to penalize extra water use during a drought. Okay, that was try number 3. All right, application example 4. Now applying. Apply a piecewise defined function. A gym owner wants to purchase custom wristbands for a marketing promotion. She thinks she will need about 75 bands. Her assistant insists that ordering over 100 wristbands will be less expensive than ordering 75. If you buy more, you get more discount. How can the assistant convince the gym owner? So look at this graph, custom wristbands order. So 0 to 50 wristbands. If you just order maybe 10 wristbands, it's going to be $2 each plus $20 shipping. Okay. And then if you order more, so 51 to 100, it's only going to be $1 each. So it's half the price and half the price of shipping. Oh, that's a really good deal. Or if you order over 100 wristbands, it's only going to be $0.5 each and it's free shipping. That's really cheap. So we're going to write a rule to represent each price point. We're going to let x be representing a number of wristbands and f of x represent total cost. And so we can write 3 different line segments, 3 different equations. So 2x plus 20, because $2 for each wristband, right? So a number of wristband is x. So 2x plus 20 is the total cost for 0 to 50 wristbands. And then x plus 10 is the total cost when you order 51 to 100 wristbands. 0.5x would be the total cost when you order more than 100. And if you graph them, okay, you graph them from here to here, here to here, here to here. It looks a little bit different than other piecewise defined functions, right? But it's fine. Look at the total cost. So if you order only 30 wristbands, it's gonna cost 30, 80, so $80. But it only costs $80, right, to order 70 wristbands because of the discount. So we have another point with the same value of y, 70, 80, right? So if you're gonna pay the same price, $80, if you're gonna spend that much money, it's better to get more wristbands, right? So this graph is really helpful for you to figure out, oh, is this worth the price, right? If you're only gonna buy maybe 10 wristbands and you're gonna pay $40, that's fine if you don't want to pay an extra $10 or $11 to get more than 100 wristbands, right? But that's a really good deal. So this graph tells you how it helps you to choose the best solution for this purchase. So the gym owner will spend less if she orders more than 100 wristbands, right? The cost for 75 wristbands is $85 and cost for 101 wristbands is $50. So she's actually saving money if she orders more. Isn't that crazy? Yeah, sometimes it happens. So make sure you do the math before you buy a big purchase. Try number 4. What is the difference in cost between one order of 200 wristbands, 2 orders of 100 wristbands each, and 4 orders of 50 wristbands each? Can you compare the prices? First of all, how could it be cheaper to buy 101 wristbands than 75 wristbands? Because that doesn't make any sense, right? But you see that if you buy more than 100 wristbands, it's free shipping. So without the shipping costs, it saves a lot of money. So sometimes it happens. How can this still be considered a function? Is this still a function? Does it look like a function? It looks like the values on the y-axis repeat, right? Like we have the same y values, but that's okay. A function could have the same y values. It just can't have different y values for one x value. Does that make sense? So if you do a vertical line test, it's all the x values will have one answer. Just one answer. So this is still a function. So answering try number 4. The cost of one order of 200 wristbands would be what? You're going to use the third equation, right? 0.5 times 0.5 times 200, which is $100. Okay. What about 100 wristbands each? So you're going to buy 100 wristbands and then another order of 100 wristbands. So you need to pay twice, right? If you buy 100 wristbands, it's not going to include on the third equation. It's going to be at the end of the second equation. So that's going to cost 100 plus 10, 110, right? So 2 orders of 110 would be 220. Yeah. So 2 times x plus 10, right? 2 times 100 plus 10 would be 2 times 110. That's $220. And 4, okay, so that's number 2. And then 4 orders of 50 wristbands each. So they're all going to total 200 wristbands. But if you order it differently, it might cost a lot more. What about 50 wristbands each 4 times? So 50 is right here. And it's going to cost $120, right? 2 times 50 is 100 plus 20 is 120. So 50 wristbands is going to be 120. And if you multiply that by 4, so 4 orders of, let's write the equation down, 2x plus 20. So 2 times 50 plus 20 is 4 times 120. And that's 480. Right? So what's the difference in cost? Buying the first option is savings of $120 compared to 2 orders of 100 wristbands, right? So the difference would be, so let's number them. 1, 2, and 3. 2 minus 1 would be saving of $120. That's a lot of money. 3 minus 1 would be 480 minus 100. So that's $380 savings compared to 4 orders of 50 wristbands. Okay, you save this much of a money if you order 200 wristbands at one time. Maybe different people need different orders, but if they collaborate and buy it all together, they may be able to save some money. So sometimes that's why it's cheaper to buy with friends. All right, that was an example of applying piecewise defined functions in real life to make better choices. So summary, what's a piecewise defined function? They're defined by different rows for different intervals of the domain. They're in pieces. They have line segments, but they're still a function, and you cannot have a repeated x value, but you can have the same y value. All right, guys, that was lesson 2. I'll see you in the next video. Bye.